Okay, thanks, Brian. Hi, everyone. It's great to be here. Thanks a lot for joining this session. I'm João Cunha, founder and AI lead at Kipon. And I want to start navigating in this graph that I built to help us in the presentation today to start to talk about what is Kipon and what we do in Kipon. Because I think it helps frame everything we will be discussing today. Well, in Kipon, we are building AI systems powered by knowledge graphs that help organizations understand how work really happens nowadays, especially as work becomes distributed between humans and agents. And my work here focuses on modeling the systems and exploring how graphs can capture this new kind of execution and how they enable more integrated collaboration between human and non-human. And this is exactly where Neo4j comes in. We are part of the Neo4j Startup Partner Program. And as we will see today, Neo4j is an essential part of our architecture, our product architecture. And well, before we dive in, I also want to share that we will soon release, together with Neo4j, a case study covering many of the ideas I will present today, based on a real implementation at Creditas. Creditas is a leading Brazilian fintech. So if you are interested in what we are discussing today, you can follow me on LinkedIn because we will be sharing more about this case study very soon. So if you want to connect with me, I put a QR code here. You can scan this and connect with me in the LinkedIn. So let's navigate in our graph to map an overview of our talk today. First, I will briefly share our view about the shift that emerges and work starts to be distributed between humans and non-humans. Then I will show how we addressing this problem using knowledge graphs, more specifically our concept of workforce graph. I will present this concept. It's a concept by Kipon. And after that, I will go deeper into the pipeline itself. Will be the more technical part of the presentation. And I will explore how we use Neo4j graph data science algorithms to do that. Finally, if we have time, I will close with a short demo of one of our features that brings many of these ideas together. We call this feature assembly. And assembly is a system that recommends teams compositions, bring together the graph, the pipeline, and the orchestration of humans and agents, okay? So as we only have about 30 minutes, let's go to the good parts. So let's back to navigate in your graph again. Whoops. To understand what is the kind of question that we are trying to answer here in Kipon. It's a simple but at the same time very complex question. It's about how do human and non-human agents can collaborate. Because up to now, work has been organized around the person as the basic unit. As you can see, roles, org charts, performance management, hiring, everything assumes that work is executed primarily by individuals. But AI agents break this assumption. We are no longer performed only by people. Work in general are no longer performed only by people. And once this happens, we need to change how we organize the work because simple roles, job titles, org charts, this kind of stuff aren't enough anymore. And we need a new unit to understand work, one that can connect people and agents through a common language that allows them to interact. But we have a problem. And let's look for our problem here. And because the workforce solutions were never designed to deal with this new reality. They don't really understand how non-humans agents integrate into work or how to model collaboration between humans and AI. The non-human agent performs real work. It contributes to outcomes, collaborates with people, but that work is invisible to the systems. So we have a thesis for approach this question. We are developing this thesis for the last 2 years. And in our thesis, skills are a strong answer to this problem. We've been thinking about skills as the minimal unit of execution, regardless of who or what performs it. This gives us a common language to redesign work around execution itself, rather than around who performs the task. Because roles change, people move, agents evolve, but the capability to perform a task remains stable as a concept. And skills is also observable. It can be inferred from work signals, outcomes, contexts. And another important characteristic of skills is that they are composable. Work is not done by a single skill, but by a combination of skills interacting. So if you want to understand work in this new structure, you need to this kind of unit that is stable, observable, and composable. And for us, this unit is a skill. And we manage this kind of approach with this this concept. I'm looking this at the graph. This concept, proprietary concept for Kipon, the workforce graph, that is the foundation of our system. Because once you try to represent skills in context, connect to work outcomes, agents, you are no longer dealing with isolated attributes. We are dealing with relationships. And this type of structure doesn't fit well in tables. Anyone who has worked with relational database here knows what I'm talking about. Graphs are the natural fit for resolve this kind of problem. Queries that are extremely hard in relational models become very simple with graphs. For example, if you want to identify single points of failure, if you want to find breeds between skills clusters, if you want to understand project skills gaps for future other projects, for example, this kind of stuff is very hard with the relational models, but it's very simple with using graphs. So we diving in the context of your workforce graph now. Oops. Yeah, let's look how it's working. In a high level, the workforce graph connects any important data to understand and orchestrate the work. So instead of saying, for example, this person has this skill, we model things like this person applied a given skill in a specific project in collaboration with other agents, producing a certain outcome at a specific point of time. It's a very different approach, yeah? So you start to see patterns like how capabilities develop across different contexts, which agents improve or replace in certain human capabilities. And because everything evolves over time, the graph isn't static. It's updates in real time as new work happens. And I want to, I think that I don't have time to answer the questions, but I don't know, someone asked about how we present these concepts. And I want to talk about two important concepts for us: connectors and ontology. So let's look for connectors in our graph now. Ontology, yeah. Connectors is a very important concept because is what allows to reflect, it's what allows the graph to reflect the real work in real time, where the work real happens. With connectors, we can connect the graph to the sources where work actually happens, like project management tools, GitHub, Slack, shared drives, traditional HR systems, and any other tool where execution signals are generated. Instead of asking people to manually declare skills, the graph observes signals from real execution. For example, commits, tickets, reviews, feedbacks, deliveries, all of this, and all of these stuffs become evidence. But ingesting data is not enough. And this is where ontology becomes critical. We don't have time to dive in this topic, but it's a very interesting topic because we need to structure those signals into a consistent semantic model that allows us to connect them in a coherent way. When we query the graph, the way information is connected, and this is the ontology, this is what will impact the performance of the inference that we can extract from the graph. And at Kipon, we use a proprietary ontology inspired by RDF principles. We follow a subject, predicate, and object structure, which is a classic structure for ontologies. And in practice, the simple models works really very well for us. Another important design choice we made was to minimize the numbers of relations types that we use in the graph. This allows us to keep the model flexible, extensible, and easier to reason about. So now I will show the real use case of assembly. So let's look for assembly now to exemplify everything we've described so far. Assembly is the flow used to recommend custom team compositions based on a high-level description of a problem. So the goal is to take an input that the user brings, something like a business need, a project idea, or an initiative, or whatever, and translate that into a structured understanding of work that needs to be done. The fine output in this feature is a recommendation of a hybrid team combining human and agents, along with the rationale behind it. It's clear which skills are needed, where they come from, and how they connect to the work. At the most basic level, this means answering questions like who has the required skills for this job, for this team, where those skills were actually demonstrated, and which parts of the work could benefit from hybrid execution with agents. But if we go further, the questions become more complex. We need to try to understand who works well with whom, which parts of the process can be fully automated, if are there hidden gems in the graph, yeah, and who could replace whom if someone is not available. More complex questions that we can find some answer if we use this pipeline that I will show now. This will be the most technical part of the presentation. So I will describe the pipeline that we use in assembly to find these answers, okay? So let's go to pipeline, and then if you have time, we will try to do a demo of this feature. What we are doing here is transforming an unstructured input into a grounded subgraph, and then running graph data science algorithms on top of it to produce a ranked and explainable recommendation. First, what we do is everything is start with the interaction of the user. So the user talks with a voice agent. This process uses a voice agent, so it's very natural. The user talk with these agents about his projects, his or initiatives, or we are trying what the user are trying to build. And we use LLM to generate a first hypothesis about the best conditions to do this work and compose this team. At this stage, what we have until now is a semantic representation of the inputs. We are trying to understand what are the jobs to be done, which skills are likely required, and what kind of context we are dealing with. But this is still ungrounded in the real work. This is just a good hypothesis made from LLMs, okay? And the second step is to try to connect this hypothesis with the real work, with the data that we have in the graph and that represent the real work. And we do this through a combination of strategies. First, we use lexical matching, direct matches, and full text search to find exact or close reference between, for example, skills. Then use vector similarity to capture semantic matches when the wording is different but the meaning is the same. And finally, we validate these matches structurally, checking how well they connect to the rest of the graph. So at the end of this step, we don't create new entities in the graph. We resolve everything against the existing graph. Yeah? Skills are matched to existing skills nodes. Contexts are grounded through the connections to projects, domains, and teams. And signals are linked to actual execution already present in the graph. So what we're trying to do here is ground the first hypothesis into the real work that are represented in the graph. This step is critical because it ensures that everything we use from this point forward is anchored in the real organization data. So the next step is create a subgraph projection, because we are if we are trying to work with the entire graph, we will have so much data that we can find the right connections, and this could be very expensive. So we built a subgraph that includes candidate skills, related projects and contexts, connect profiles and agents, and relevant execution signals. So this subgraph becomes the computational space where all downstream analysis happens. And this is an important idea. We are not running algorithms on the whole graph. We are computing on a context-specific projection of it to be more precisely. So we go to the next step where we, in fact, try to find the candidates for this team, this ideal team. And to do that, we combine three different approaches. We use vector similarity to capture semantic proximity, matching skills and profiles that are conceptually similar. We expand the graph using K-hope to capture structural proximity, who can be close of other person, not in a semantic way, but in a structural way. And we use node similarity to identify profiles that share similar neighborhoods, people who have worked on similar projects or have similar skills, for example. In some cases, we can also use embedding techniques like FastRP to combine these both approaches, but we are now testing this kind of process. The result of this step is a candidate set that is semantically relevant, structurally grounded, and context-aware. Once we have this candidate set, the problems shift. Now it's about ranking this group. And this is where GDS become more central for us. We compute multiple signals over the subgraph. We can use PageRank to measure influence. We can use similarity metrics like Jaccard to measure overlap between required skills and observed capabilities. We can use Louvain to understand how skills and collaborators clusters together in this context. Each of these algorithms captures a different dimension of relevance. Can be similarity, importance, connective. So we are trying now to explain the steps that we are passed through to get these conclusions. So this is a benefit of the graph, because we can explain exactly what was the steps that we need to go through to get our informations or get the perfect match to the composition of this team. So finally, we work with pipeline to scoring the suggestions and finally compose this team. We combine all the signals that we compute until now and use some kind of algorithms to optimize this process, like complementary skill convergence, structural diversity, and collaboration compatibility. Finally, we add one more layer to try to understand how agents can compose this team together. Yeah. So until now we had just persons in this team, and now we will understand how we find agents that can augment some capabilities of some person, or in other scenarios can automate a process, whole process. Okay, so we already have 5 minutes, and I will try to do a demo of this feature assembly. The demo that I will show is a demo in production. So we use all these passes, these algorithms, and this process that I show you to get the final match of the chips. Okay. So let's try. I think you are already seeing this screen. Everybody seeing the screen of the feature? I don't know. Okay, no. Okay. So I will start to conversate with this agent, and it will try to help me organize my ideas to understand what I want to do. So let's start.
will only take about 2 minutes to get started. Just tell me in your own words what you're trying to build.
Now we are trying to build here in Kipon an knowledge graph that can represent the real data of the work.
That sounds like a very interesting and valuable initiative. To help me understand it better, could you tell me what problem or opportunity this knowledge graph aims to address for Kipon?
We are trying here to build a system that suggests skills in a more effective way. And we understand that graphs can help us to connect this data to find the right skill for the right person.
That's a clear objective. So the core idea is to use a knowledge graph to improve skill suggestions by connecting data more effectively. To achieve this, what are the main work streams or phases you envision for building this knowledge graph and integrating it into a skill suggestion system?
I think that you got it, the idea. So I will pass through the next step because we don't have time. But now we process all the conversation and find the main data that will help us to build this team. So, for example, we describe here the initiative, the objectives, the jobs to be done. We list the jobs to be done. What is the kind of skills that we need to address these jobs to be done? If you have relevant projects or relevant teams, people that are part of relevant projects and teams to help our intelligence to build this team. So we are processing the data now through this pipeline that I showed. And the result is that we have suggestions for the composition of this team. For example, Rico is the co-founder of Kipon that lead with more technical things and are a specialist in ontology too. So as you see, we understand why Rico was suggested, because Rico are participated in a relevant project. He could have some important skills, and we suggest yet agents and skills that can combine with human knowledge to compose this team. Okay. So I don't know.
That's a very comprehensive overview of your program.
So we have more 1 minute, and I don't know if someone have some question. Let me see in the queue.
I understand you're explaining your internal.
Okay. Could you share a bit more about how you create the ontology? We base our the process to create the ontology in RDF, but we are trying a lot of systems and process that already exist to create ontology. But at least an ontology needs to work for we are trying to resolve, yeah, the context that we are trying to lead with. So we create our own ontology because we understand that neither ontology of already exists represent it's specifically for represent the work, the workforce. So if you are leading with a very specific context, I suggest that you create your own ontology. So I think that we don't have more time. You can connect with me in the LinkedIn, so we can extend this conversation in other places. We can do calls or wherever you want. Okay.